In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 80. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with the formation of acids in oil directly affects polarization losses. Oxidative degradation of transformer oil leads to the formation of organic acids which elevate the concentration of polar species and colloidal products in the oil. This results in a considerable increase in electrical resistivity and corresponding increase in dielectric losses, especially in the low frequency region. Oxidation process of the nonpolar mineral oil would have been accelerated under the influence of heat, oxygen, moisture, and metal catalysts like copper. The polar compounds is produced along with moisture and sludge, significantly increase the dipole relaxation polarization under an alternating electric field, increasing the dielectric loss angle. The oxidation of transformer oil, basically mineral based, produces carboxylic acids which are classified into two main types based on their molecular weight and solubility. One, low molecular weights, another is high molecular weight acids. Low molecular weight acids, that is formic acid, HCOOH, acetic acid, CH3COOH, propionic acid, that is CH2CH3COOH, sorry, CH3CH2COOH, and levulinic acid, that is C6H8O3. High molecular weight acids, that is naphthenic acids. Furthermore, oxidative reactions generate water as a byproduct, which is a strong polar substance that significantly increases ionic mobility and polarization, leading to higher dielectric losses. As transformer oil oxidizes, it produces low molecular weight and high molecular weight organic acids. However, the characteristics of low molecular weight acids as compared to high molecular weight acids are quite different, mainly in their volatility, solubility, and impact on insulation. Low molecular weight acids have smaller molecular sizes, while high molecular weight acids consist molecules relatively of larger in size. Low molecular weight acids are highly hydrophilic and strongly attracted to the cellulose, that is paper insulation, cellulose based paper insulation, whereas high molecular weight acids are hydrophobic but readily soluble in oil, less aggressive, and contribute to sludge formation. The presence of both types of acids in transformer oil would thus to indicate an advanced stage of oil aging and deterioration of its dielectric properties. Once the concentration of acidity and associated degradation by products such as sludge and moisture reaches at critical threshold levels in transformer oil, it indicates that the oil paper insulation system has entered an advanced stage of oxidative and chemical degradation. This condition must have to demand a definitive trigger for urgent maintenance actions such as oil reclamation or regeneration or replacement to prevent severe and irreversible damage to the transformer's internal insulation and structure. Impact of low molecular weight acids on paper insulation. Low molecular weight acids, specifically formic, acetic, and leuvenec acids, are highly polar compounds and have an affinity with cellulose paper, cellulose-based paper insulation and water because of their ability to form hydrogen bonds with the hydroxyl group in the cellulose structure. Low molecular weight carboxylic acids containing up to 5 carbon atoms, such as formic acid and acetic acid, exhibit higher polarity and hydrophilicity. Due to their greater solubility in the moisture phase within the oil paper system, they preferentially migrate into the cellulose insulation and significantly accelerate acid catalyzed hydrolysis, thereby increasing the rate of depolymerization of the paper. Electrical grade insulation paper and pressboard would have to contain more than 90% of cellulose. Paper that provides high mechanical strength, excellent dielectric strength, and low dielectric loss, making it ideal for insulation in oil-filled transformers. However, pressboards are mainly made of soft wood tree with having long fibered structure and of high purity cellulose. The long fibers are crucial for creating high density and mechanically strong pressboards that resist shrinking and maintain structural stability in transformers. There are mainly three mechanisms are responsible for irreversible degradation process of these paper insulations in transformer, which include 1. Acid hydrolysis, 2. Oxidation, and 3. Pyrolysis. Out of the carboxylic acids as formed in transformers, the low molecular weight acids such as formic, acetic, and leuvenec acids are considered as byproducts from the acid hydrolysis of paper, which act as catalysts in paper aging. The progressive accumulation of these acids causes a substantial decrease in the degree of polymerization of the cellulose, which is directly correlated with diminished mechanical strength and structural integrity of the insulation, thereby increasing its susceptibility to embrittlement. It is evident from its chemical characteristics that formic acid produced during the degradation of transformer oil paper insulation, it recognized as more hydrophilic and chemically aggressive than acetic or leuvelinic acids. In oil impregnated kraft paper insulation system, formic acid is identified as a particularly destructive low molecular weight carboxylic acid because of its appreciable solubility in oil and strong affinity for diffusion and absorption into cellulose matrix, which significantly accelerates the degradation of the solid insulation. Key characteristics of formic acid formed during oxidative reactions in transformer oil. The formation of formic acid due to the oxidation process in transformer oil is a low molecular weight acid with particularly aggressive effects on transformers insulation system. Formic acid is a low molecular weight organic acid that is 46.03 gram per mole. Formic acid structure HCOOH is the simplest form of carboxylic acid that contains two oxygen atoms, a single carbon atom, and two hydrogen atoms. As of the diagram, formic acid features a central carbon atom double bonded to one oxygen, single bonded to hydroxyl group, and single bonded to a hydrogen atom, forming a carboxylic acid functional group COOH attached to the simplest alkyl group. Formic acid, owing to its small molecular size, is predominantly polar and has a strong hydrogen bonding capability, which thermodynamically favors its solvation in polar media such as water. However, despite this dominance of its highly polar carboxyl group, the molecule retains a very small nonpolar component. Although minimal, this nonpolar character slightly moderates its overall polarity and imparts a limited hydrophobic contribution with the nonpolar hydrocarbon matrix of transformer oil. From a thermodynamic perspective, even this limited nonpolar character can marginally improve its compatibility with nonpolar media such as oil compared with highly polar or strongly ionized species. The logic behind polar and nonpolar characteristics of formic acid. Formic acid is highly polar is due to the presence of highly electronegative oxygen atoms in the carboxyl group. These oxygen atoms create strongly polar content bonds, resulting in partial negative charges on the oxygen atoms and partial positive charges on the carbonyl carbon and hydroxyl hydrogen. The hydroxyl, that is OH group, is highly polar and forms strong hydrogen bonds with water, making molecules much more hydrophilic and increasing their overall polarity. As this polar bonds are not being cancelled out, resulting in a strong overall molecular dipole, making it a highly polar molecule. But formic acid of having single OH group is less polar than that of water or alcohols, where both are being constituted with multiple OH bonds, OH groups rather. However, formic acid is slightly nonpolar relative to some other extremely polar compounds such as pure water or a simple alcohol like methanol. Compared to other carboxylic acids like acetic or butanoic acid, formic acid has a very small nonpolar component as its molecule possesses just one hydrogen atom bonded to the carboxyl carbon. Therefore, the solubility level of formic acid in nonpolar solvents like transformer oil is limited as compared to all these hydrocarbons. But the presence of dissolved formic acid in insulating oil introduces strongly polar functional groups into an otherwise nonpolar hydrocarbon matrix like transformer oil. Underneath factors that can be concluded that can be concluded by analyzing the internal structure and polarity of the bonds within the formic acid. Formic acid, number one, formic acid that contains a hydrogen atom directly bonded to a carbon atom and a hydrogen atom bonded to an oxygen atom. The CH bond is mostly polar covalent. That's because there would have a small electronegativity differences around 0.3 between carbon, that is 2.5 electronegativity, and hydrogen 2.2. The electron withdrawing power of the oxygen atoms has met to draw electron density away from the carbon, which in turn pulls electron density from the hydrogen. Due to differences in electronegativity between the bonded atoms, both the carbon-hydrogen bond and the oxygen-hydrogen bond are classified as polar covalent bonds. Polar covalent bonds. Number 5, it is thus to understand that the OH bond is significantly more polar than the CH bond because oxygen is substantially more electronegative than carbon, which is itself slightly more electronegative than hydrogen. Therefore, such type of arrangement of these bonds is not at all symmetrical. So, the individual bond dipoles do not cancel each other out. Based on the molecular structure and bond polarity of formic acid, the single hydrogen atom bonded to the carboxyl carbon constitutes a small, relatively nonpolar region in clear contrast to the highly polar OH bonds. Nonpolar, a very weakly polar character, nonpolar or very weakly polar character arising for the presence of single CH bond would have a negligible impact on the overall polarity of the formic acid. Number 9, such character is almost entirely overshadowed by the strongly polar carboxyl functional group. The behavior of its molecules is overwhelmingly governed by its high polarity and strong hydrogen bonding capability. Number 11, it is important to note that the formation of formic acid in transformer insulating oil is significantly more injurious to the paper insulation system than acetic acid and other higher molecular weight acids due to its higher chemical strength and greater absorption rate into solid insulation. Effect of polarity contrast on electrical response of insulating oil. This polarity contrast significantly alters the electrical response of the insulating oil, closing to contribute underneath impacts. 1. Enhanced dipolar polarization under an applied electric field, whereby permanent molecular dipoles attempt to align with the field, that is electric field, leading to energy absorption. Impact of number 2, impact on degree of polymerization, especially at low frequencies. Number 3, reduced volume resistivity due to enhanced ionic dissociation in the presence of moisture. Number 4, impact on overall breakdown voltage of the oil. Number 5, reduction of the interfacial tension, which is a key indicator of oil degradation and contamination. And last one, 6, formic acid is hygroscopic, meaning it attracts and retains water in the oil, further degrading the dielectric properties. 1. Enhanced dipolar polarization. As a polar impurity dissolved in the nonpolar mineral oil, formic acid molecules possess a permanent dipole moment that attempts to align with the applied alternating electric field. B, because dipolar alignment cannot follow the field instantaneously, a phase lag develops between the induced polarization and applied field. This phase displacement signifies that a portion of the electrical energy supplied during each cycle is not stored elastically, but is instead absorbed by the medium that is oil and dissolved acid. Again, I repeat, this phase of displacement signifies that a portion of the electrical energy supplied during each cycle is not stored elastically, but is instead absorbed by the medium, that is oil and dissolved acid. The absorbed energy is subsequently dissipated as thermal energy, which is rather measured as dielectric loss. This phenomenon manifests as an increase in dielectric loss, that is tan delta, particularly in the low frequency region where the dipolar and interfacial polarization mechanisms govern the dielectric response. Number 2, impact on degree of polymerization. Formic acid acts as a critical degradation component in power transformer oil paper insulation systems, functioning as both a primary byproduct of cellulose aging and a potent catalyst for further degradation. While insulating paper, cellulose-based insulating paper, undergoes thermal stress, it starts to degrade and simultaneously releases low molecular weight organic acids, with formic acid being a major component. The accumulation of organic acids decreases the local pH value of the paper oil system, thereby catalyzing additional hydrolysis of glycosidic bonds in cellulose and accelerating the reduction in degree of polymerization. Number 3, reduction in volume resistivity. Volume resistivity in transformer oil is the key parameter to measure its ability to oppose or resist the flow of electrical current through its bulk, which it is generally expressed in ohm centimeter. So, it is a crucial indicator of justifying the oil's insulating quality, purity, and aging criteria. Higher resistivity signifies cleaner, less degraded oil with better dielectric strength, while lower values indicate contamination, moisture, or degradation. The the oxidative reactions in transformer oil and the hydrolysis of proper insulation generate low molecular weight carboxylic acids, particularly formic acid, which is a dominant product in early stage of degradation. Formic acid, a polar compound whose accumulation in nonpolar oil component that creates to enhance the concentration of polar species, which directly increases the conductivity of the oil. As the acidic species promote partial ionic dissociation, especially in the presence of moisture, thereby increasing charge carrier concentration and ionic mobility. Formic acid is highly soluble in water, that is miscible, and despite being polar, polarity index of 6.0 exhibits partial solubility in non-polar hydrocarbon insulating oils, that is mineral-based insulating oils. Formic acid has a high dielectric constant of 58.5, which is significantly higher than that of insulating oil, often leading to increased polar component in the oil-acid mixture. Such phenomenon tends to concentrate the acid component at the oil-paper interface, where it interacts with polar cellulose chains. However, the impact of formic acid in the dielectric properties of transformer oil is significantly magnified in the presence of moisture. Formic acid generated as a byproduct of cellulose aging interacts strongly with water molecules to facilitate ionic dissociation within the oil paper insulation system. This phenomenon is commonly referred as acid hydrolysis, which breaks the cellulose polymer chains, causing a significant reduction of the mechanical and dielectric strength of the cellulose-based paper insulation. Simultaneously, the combination of acids and moisture elevates the concentration of mobile ionic charge carriers and enhances ionic mobility within the oil paper system, thereby increasing electrical conductivity and reducing the bulk resistivity of the insulating oil. Number 4, impact on overall breakdown voltage of the oil. The contrast in polarity between the insulating mineral oil, which is nonpolar, and oxidation products, which is highly polar, causes an obvious distortion within the electric field, leading to a drastic reduction in dielectric strength. The dielectric strength is the maximum electric field an insulating material can withstand without breaking down and becoming conductive. The breakdown voltage of dielectric material is serving as the key indicator of this withstanding capacity. So, the breakdown voltage is one of the most critical parameters in evaluating the quality of the insulating material. This parameter has to indicate how much voltage the material can withstand before dielectric failure occurs. The insulating paper as used in the transformer consists of about 80% cellulose, 12% hemicellulose, and 8% lignin and certain mineral substances. It has already been exhibited that the acid hydrolysis is a primary mechanism for the degradation of cellulose, where the process is highly dependent on the presence of both water and acids. Cellulose degradation process, once started, this will generate more low molecular weight acids such as formic and acetic acids, which will remain absorbed in paper and accelerate the degradation of cellulose in turn. Acid hydrolysis process is rather considered a self-accelerating or autocatalytic process as the newly formed acidic compounds will further catalyzing the cleavage of remaining glycosidic bonds of the cellulose. Cellulose degradation via acid hydrolysis is a critical chemical process that leads to a progressive reduction in the degree of polymerization of cellulose. The degree of polymerization of cellulose represents the average number of glucose monomer units in linked together in a cellulose chain and serves as an indicator of the molecular chain length. For oil impregnated kraft paper used in newly manufactured power transformers, the initial degree of polymerization typically lies within the range of 1000 to 1200. The range may have to reflect the long chain structure, which is necessary to ensure adequate mechanical strength and durability at the time of commissioning. A reduction in the degree of polymerization of cellulose is gradually driven by the chemical degradation mechanisms such as acid catalyzed hydrolysis or oxidative reactions and oxidative reactions. Sorry. At elevated operating temperatures, the rates of these degradation reactions would have to increase exponentially, which is thereby accelerating the reduction in degree of polymerization. This exponential increase in reaction rate is fundamentally explained by the Arrhenius equation. Arrhenius equation, which indicates that the higher temperatures provide reactant molecules with significantly more kinetic energy. And aging progresses when the degree of polymerization of cellulose drops below approximately 200 to 250. It is generally accepted as a critical indicator of end of life for cellulose-based materials, particularly electrical insulation paper used in transformers. As the cellulose insulation undergoes thermal, oxidative, and hydrolytic aging process, it releases harmful byproducts such as water molecules, organic acids, and solid particles that migrate into the surrounding transformer oil. Those byproducts consist predominantly of polar compounds, which increase the oil's overall polarity, acidity, and ionic content, thereby accelerating secondary oxidation and polymerization reactions within the oil phase. The acidic contaminants, especially organic acids and water, in the deteriorated oil further promotes cellulose depolymerization and hydrolytic cleavage of glycosidic bonds. This mutual interaction establishes a self-perpetuating degradation cycle between the oil and the paper insulation systems. A degradation of cellulose paper insulation in power transformers characterized by a reduction in the degree of polymerization does not directly reduce the dielectric strength of the oil. Rather, it promotes the formation of moisture and acidic byproducts that deteriorate the oil's dielectric properties. It is therefore evident that the degradation of paper insulation, as indicated by a reduced degree of polymerization, correlates with an increase in harmful chemical species in the oil, which consequently leads to a reduction in breakdown voltage. Reduction of the interfacial tension. Over prolonged service life, transformer oil may progressively exhibit increased polarity contrast as polar degradation products accumulate. These polar species, these polar species arise mainly from additive oxidative aging, moisture ingress, and oil paper interfacial reactions, leading to a gradual shift in the physical and chemical characteristics of the overall insulation system. Changes in the physical characteristics of solid and liquid insulating materials, including structural configuration, thermal stability, and mechanical strength, which directly affect their form, density, and overall functional behavior. Changes in chemical stability, including resistance to oxidation, corrosion, and acidic degradation, alter the molecular structure of the insulation materials. In cellulose insulation, these manifests as a reduction in the degree of polymerization, whereas in insulating oil, increased chemical reactivity influences dielectric breakdown strength, acid number, interfacial tension, and water content. The polarity contrast, as developed in transformer oil, promotes interfacial interactions by lowering the interfacial tension between the nonpolar oil matrix and polar species such as water and oxidation byproducts, thereby facilitating dispersion and interfacial charge phenomena. Let's stop here, further to be continued at the later stage. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, please let me know in the comment section, please. Thank you. Thank you for patient hearing.